Alright, hello 8-bit physics students. Got a great problem for you tonight. Chapter 19, problem 17. I'm so excited. We got circuits, we got voltages, we got resistors in parallel, resistors in series, equivalent voltages, Kirchhoff's loop rules. Oh, I am pumped. Let's dive in. So problem 17, I have three resistors arranged in a circuit like this with a 12-volt battery. And in the book, they're just called the 680 ohm resistor, the 820 ohm resistor, the 470 ohm resistor. Well, I'm going to call them 1, 2, and 3 because I don't want to say 470 too many times. That's too many numbers for me. So part A of this problem says calculate the equivalent resistance of the circuit. And part B says find the voltage drop across each three of these resistors. All right. So let's go ahead and get to work. I notice here that R1 and R2 are in parallel with each other. And not only are they in parallel with each other, but they're just kind of off by themselves here. You might say, hey, isn't R3 in series with R1? Well, not really. R3 is in series with the two of these together. But really, I would have to look at R1 and R2 together first. So I can use my rules for finding equivalent resistances for resistors in parallel. And it's the inverse of the rule for, this should be R1 plus R2, but you get the idea. It's the inverse of the rule for series. So if I wanted to find the equivalent resistance here, I would do 1 over 820 of R1 and R2. 1 over 820 plus 1 over 680. I would take that answer and then take the reciprocal of it. Excuse me. So let's do that, and we're just going to bust out the calculator here because I don't really want to find a common denominator for 820 and 680. So here's a little trick. 1 over 820 plus 1 divided by 680. That's the answer, but that's not really the answer because that's the inverse of the answer, right? So I'm just going to take that number to the negative first power, meaning the inverse, and boom, there it is, 371.7, let's call it 372. So the equivalent resistance of R1 and R2 is 372 ohms. Now what I'm going to do here is I'm just going to go ahead and redraw my circuit, okay? I now have a circuit that looks like this. Instead of 3 resistors, it has just 2. A 372 ohm resistor and a 470 ohm resistor. But what happened to these two resistors? Well, what I'm saying is if I take out those two resistors and replace them with just one resistor, it would be the same circuit. So we say these would be two equivalent circuits. All right. Well, what do I have now after I've done the equivalent resistance of those two? Well, now to find the equivalent resistance of these two resistors, which are in series, right, I would use the equation for series. So the equivalent resistance for resistors in series is, and I'm going to call this R12 plus R3, okay? I just add them up. So I do 372 plus 470, and I get an equivalent resistance of 842 ohms, okay? And I'm going to redraw my circuit again, okay? So now I've gone from 3 resistors to 1 resistor, and this REQ here is 842 ohms, okay? So you kind of got to go step by step saying, all right, what resistor is in series or parallel with what resistor, okay? Now, so far, this is the answer to part A, right? The answer to part A is what is the equivalent resistance of this circuit? Well, the equivalent resistance is 842 ohms. So I could take out these 3 resistors and replace them with one resistor of 842 ohms. Well, part B gets a little more complicated. Part B says find the voltage drop across all three resistors. Now, the voltage drop is not going to be 12 volts. The overall voltage drop will be, but individually these guys are going to be different. Now, to do this, I'm going to have to label some currents. I'm going to label the current in this branch of the circuit I3, meaning the current going through resistor 3, okay? The current here is going to be I1, the current going through R1, and the current here is going to be I2, meaning the current going through R2. Now, one important idea here is Kirchhoff's junction rule. Junction rule. We talked about the loop rule last time. By the way, I think last time I misspelled Kirchhoff. I used one H, so it is two. Kirchhoff's junction rule says this: the current flowing into a junction must be equal to the current flowing out of a junction. In other words, electrons don't just randomly disappear. So if I look at I3 here, the current flowing into the battery and the current flowing out of the battery, I3 flows into this junction, and the electrons split. Some go this way, some go that way, but the overall number of electrons that go into that junction equals the number that goes out. Okay, so that's the junction rule. All right. Okay. Well, I already know what I3 is. Okay, I3 is the current that goes out of the battery and into the battery, right? Well, from this equivalent circuit here, I can use Ohm's law to say I3 is equal to V over Req. All right? Because this is current out of the battery and back into the battery, I3. So I3 would have to be 12 divided by 842. Okay? And if I do 12 divided by 842, I get 14.3 milliamps, or 0.0143 amps. Okay? So that is the current going out of the battery and the current coming into the battery. It is also the current that runs through R3. Okay? Well, I can use Ohm's law yet again and state that the voltage drop across resistor 3 has to equal the current going through resistor 3 times the resistance of resistor 3, right? This is just Ohm's law rearranged, and instead of applying it to the whole circuit, I'm just applying it to resistor number 3. So this is 0.0143 times 470, okay? And that turns out to be, what does that turn out to be? 6.70 volts, okay? So what this is saying is, when looking at the battery here, the battery is upping the voltage 6.7 volts, and this resistor R3 is bumping the voltage back down 6.7 volts, okay? Now, we could try to figure out what I1 and I2 are, but let's just use our loop rule instead, okay? Kirchhoff's loop rule says the voltages up must equal the voltages down around any loop. So, for instance, if I wanted to, there are some electrons that go out of the battery into R1 and back into R3, right? This in here is a loop, okay? So what I can say here is that V1 would have to equal the overall voltage minus the voltage drop across V3. In other words, V1 would have to equal 12.0 minus 6.70. In other words, V1 would have to be 5.30 volts. Okay? So I go through if I'm an electron, or let's say I'm a bunch of electrons that have a charge of 1 coulomb. as I go through the battery, this 1 coulomb of charge gets 12 joules of energy. Well, if I get 12 joules of energy as I go through the battery, and I lose 6.7 joules of energy when I go through R3, how many joules of energy must I lose when I go through R1? I must lose 5.30 joules. Notice, by the way, that an electron either goes through R1 or it goes through R2. It doesn't go through both in the same loop. So likewise, we could say, so this is our answer for the voltage drop across resistor 3. Resistor 1. This was our answer for the voltage drop across resistor 3. By similar logic here, we could say that if an electron, instead of going along this loop, went along this loop, it must also have a voltage drop of 5.3 volts. In other words, V2 must also equal V minus V3, so V2 must also equal 5.30 volts. Okay, so the voltage drop across two resistors in parallel will always be the same. Now, if we had extra time here, we could go through and verify Kirchhoff's junction rule by going through and calculating the current in I1 and I2 by using the voltage drops and the resistances we've calculated. And lo and behold, if I look at the current in branch 1 plus the current in branch 2, lo and behold, do those two currents add up to be I3? Why, yes, they do. Okay? So you don't have to show that for the problem, but there it is. All right, tough problem. Way to go, physics students, for your moment of inspiration here. I have a little cartoon for you from Chicken Soup for the Teacher's Soul. And it goes like this. This is really hard physics we're doing, so just keep in mind that you're going to make some mistakes, but trying hard and making those mistakes sometimes helps you learn more than anything else. So here's our laugh and joke of the day. Teacher, can I borrow one of your pencils? Mine has all the wrong answers in it. I remember a lot of days in college studying physics where I might have felt like that, but it really does help you learn a lot challenging yourself. All right, nice work, physics students. We'll see you tomorrow.